Next, we are going to talk about the effects that have on the rate of the SN2 reaction. Basically, what are the factors that affect the rate of SN2 reactions? First one is substrate effect, the structure of alkyl halide. The second is nucleophilic strengths. What kind of nucleophiles are there, and which one is stronger, which one is weaker, and what determines the strength of nucleophiles. First, it's good to start with this table, and before we start, we have to say that the rate of SN2 reaction is extremely sensitive to the structure of alkyl halide. And as you can see, we use this as an example reaction. We have a bromide as a starting halide, and we use sodium iodide as our nucleophile, basically iodide minus iron, in acetone as a solvent, room temperature. Basically, iodide replaces bromide. That's very simple SN2 reaction. And they have measured the rate with different substituents. And then two trends have been observed. So let's start with trend number one. And as you can see here, if you increase the number of substituents at alpha position, the rate substantially decreases. So here I have my alpha carbon and there's no any other alkyl group. So this is methyl, 0 degree. This is primary, this is secondary, this is tertiary. And as you increase the number of substituents, basically number of beta substituents, rate decreases dramatically. That's the first trend that we have to talk about. And this gives us this kind of trend of reactivity. So methyl halide is the most reactive when it comes to SN2 reaction in compared to secondary and tertiary. Tertiary is basically unreactive. We never see tertiary alkyl halide reacting with some nucleophile according to SN2 reaction. That never happens. And that's the first trend. And second trend is we have number of beta substitutes increasing from top to bottom and rate is decreasing again. But as you can see here, they are all primary, right? Because they have one beta substituent attached to alpha. So they are all primary, but here we are actually interested in number of gamma substituents, number of substituents that are attached to beta. So they are increasing and the rate decreases, but as you can see, the decrease in rate is not as significant as the decrease of rate is observed in the trend number one. So this is only a moderate effect, not very sensitive, not very significant as increasing the number of substituents in alpha position, but still it affects. And we can explain both of these trends by exploring the structure of the transition state. But before we move on, I have to just explain this. All the rates are relative to the rate of reaction between ethyl bromide and iodide. So they have used ethyl bromide and iodide reaction as one. So that doesn't mean that that's just one, let's say, molar per second or something like that. It's just some value, but then they have divided all of them by the rate of the reaction for ethyl bromide, and they chose ethyl bromide rate as relative rate as 1, and that they all are relative to this ethyl bromide. So this is some kind of, I would say, reference point we have to use. We have to explore the transition state. So this is the transition state that we already talked about: incoming nucleophile, outgoing lipid group. And obviously transition state in the energy diagram that corresponds to the highest point in the energy diagram, right? So if you start with nucleophile and alkyl halide, you just go to the transition state, which is the highest peak in the energy diagram. And this is the transition state. This is what the transition state would look like for this specific reaction. Carbon has a bond between cyanide and also bromide. And then you are going to form a product where cyanide basically replaces bromine. And just like with any reaction, relative energy of the transition state determines the rate of the reaction. Higher the energy of transition state, higher the activation energy gonna be, then the rate of reaction will be slow. And I'm gonna use the previous picture that we have introduced in the previous slide, this, where we have incoming nucleophile and outgoing lipid group on the same transition state, and they are both negatively charged, so we want them as separate as possible. So this is the picture we have explained the back attack. But now you can use the same picture to explain the fact that we have a steric hindrance. So we call this as steric hindrance, where we don't want negatively charged parts of the molecule to be as close to each other. So this steric hindrance explains back attack, but at the same time, this explains why certain alkyl halides react faster with SN2 reaction, but the other ones, for example, tertiary or secondary, react slower. It's because we don't want to have additional destabilization here. Because energy of transition state is already high. We are having pentavalent carbon, and we have densely like electron dense region on both sides of the transition state. But we don't want to have other alkyl groups here that are attached to alpha position that would make the transition energy of the transition state higher. So what we have to understand here is that if the transition state is high in energy, then activation energy will be large and the rate will be slow. And if transition state is low in energy, then activation energy is going to be small and the rate will be fast. So here you see the comparison between different substrates. So SN2 with a metal substrate, 0 degree, primary and secondary. They haven't even included tertiary because tertiary alkyl halides do not undergo SN2 reaction. And what we have to understand from this graph is that when you replace hydrogens with alkyl groups, you're basically going from primary to secondary to tertiary. What happens is that you have stronger steric interaction in the transition state, which makes its energy higher. And that's why you have higher activation energy and slower reaction. So your trend looks like this, where you have a carbon and you have a nucleophile that you form a bond with, and you have a leaving group that's leaving, the bond is breaking. And if you have hydrogens here, so we always have to show the transition state with square brackets and double dagger. When you have hydrogens, it's like transition state that is not affected much by these hydrogens. But let's say you make this hydrogen, you replace this hydrogen by methyl group. What's going to happen is that you basically make primary alkyl from methyl halide. And now this introduction of methyl group introduced huge electron density, electron cloud. That interferes with the electron cloud, the delta negative of the nucleophile, at the same time a leaving group that basically increases the energy of the transition state because of his steric hindrance. And let's replace other one with other hydrogen with alkyl group. And now you have one more large cloud of electron density. And why they are electron density? Because they are like, we are introducing basically 3 bonds and every bond is 2 electrons. So basically we are introducing 6 electrons here and they are electron donating groups, methyl groups. So they make this highly unstable. And as you know, stability and energy are inversely proportional. So unstable means high energy. And when you increase the energy of transition state, activation energy also increases and the rate decreases. And what's the relationship between activation energy and rate? We can find it using Arrhenius equation where rate constant equals to A e to the power of EA over RT. So reaction rate depends on K and the concentration of reactants basically, right? Reactants. And so basically rate constant depends on K and K in turn depends on activation energy. Higher the activation energy, lower the K, and lower the rate constant, lower the reaction rate. That's the reason why any destabilizing effect on transition state will ultimately result in slower reaction rate. Do you have it? We can use another example called neopentyl bromide. So this is actually primary halide, you see, because alpha is only connected to one substituent, so there's only one beta position. So this is primary alkyl halide, but this essentially does not undergo SN2 reaction. There's negligible reaction rates. You might say that, oh, this is primary is here, right? So it should undergo SN2 reaction with reasonable reaction rate, and we should get product in reasonable yields. But that's not the case. Even though this is primary alkyl halide, it does not undergo SN2 reaction efficiently. And that's the reason why it does not undergo SN2 reaction and it has negligible rate is because of transition state being really high in energy. So this is primary, but still this group is so large that is connected to beta that it interferes with the electron density of incoming nucleophile and outgoing leaving group, and that immensely increases the energy of transition state. And that's why we don't observe any reasonable reaction rates for this substrate in SN2 reaction. As you can see, it's not like we are memorizing, oh, tertiary does not undergo methyl, primary and secondary, they undergo the reaction, and in beta, it's not like that. We don't memorize it like this. We always see the structure and we explore the structure of transition state, and then we make some conclusions about the reaction rate based on the structure of transition state. Now we continue, and I would like to continue with an advanced concept here, which is effect of adjacent pi systems on the rate of SN2 reaction. So this is how it looks like. I still have substitution reaction, but this substrate is different from the other substrate in the sense that I have a double bond that is 1 sigma bond away from the reaction center, from the carbon, from alpha carbon. So we call this allyl bromide, and they have found out that allyl bromide, this is like primary alkyl halide, but it is allylic. The bromine is in allylic position. They have found out that this is actually undergoing SN2 reaction much faster than similar primary compound that doesn't have any double bond nearby. So they have provided some explanation on what kind of effect that this adjacent pi system could have on the rate of the reaction. In order to understand this, it's good to show this transition state again in slightly different diagram. So we have nucleophile with its electron. It has orbital that's filled with electron pair. And this is our substrate where we have X that's leaving. It has its own orbital, and we have a carbon orbital right here. And then we are forming new bond between nucleophile and p orbital on the carbon. And this is like p orbital. So here carbon is sp3 hybridized. But in the transition state, it's actually sp2 hybridized because it has 3 bonds and 1 p orbital with 2 electrons in it. And it's trying to make a bond with nucleophile. And the bond between carbon and leaving group is breaking. And this leaving group is leaving with its 2 electrons and with its orbital. And now we're going to form new bond. So allyl compounds here react rapidly by SN2 mechanism because in the transition state, pi system of the adjacent double bond can stabilize the transition state. So what happens here is that in the transition state, the p orbital of the carbon has to make 2 partial bonds with only 2 electrons. So it's electron deficient. So any additional electron density we could have here can stabilize transition state and can lower the energy of transition state, which means increasing the rate of the reaction. So here we have electron density on the carbon, but electron density available on the carbon that's supposed to stabilize transition state is actually not sufficient. So because this carbon here is trying to form 2 partial bonds with bromine leaving group and with OR incoming nucleophile, so it's electron deficient. So we need basically a supply of electron density from nearby. So this pi system has pi bond, it's sigma and pi bonds, double bond, so it is very electron dense, and that additional electron density helps to stabilize this transition state and lowers its energy, ultimately making reaction much faster. And now we can quantify structural effects with using this as an example. This is just similar to the tables trends that we have introduced in the beginning, but it's more advanced in a sense that now we will have allylic as well. So here, as you can see, methyl chloride is the fastest because it's least hindered. So it's like chloride, right? It's 0 degree alkyl halide. So it's the fastest. And this is a bit steric hindrance because of the alkyl groups. You basically replace hydrogens with alkyl groups, and that increases the energy of transition state, which decreases the rate of the reaction. But here, rate increases again because you have adjacent pi system. And by the way, benzene's pi system is much better in terms of stabilizing the transition state. So you have even better pi conjugation here. And this guy here has the best pi conjugation, and it has really large rate, number of reaction rate. Okay. You see this is 0 degree. So this is the fastest. So there is no steric hindrance at all. So the energy of transition state is really low. So this is 0 degree. But this is primary, first degree, right? So we know that the 0 degree, and I call methyl as 0 degree, by the way. Methyl is higher in terms of reaction rate, is higher than first degree, and this is second, and then this is third, right? So we expect this 0 degree much faster than first degree, right? But then, as you can see, they have the same rates. So it's because of pi conjugation. Even though it's primary, it's a bit sterically hindered, but then I have stabilization factor here from the conjugated pi bonds. So that actually results in methyl chloride having the same rate as conjugated primary halide. Now there's a question. They ask us to draw a transition state. So we have a substrate and SH is our nucleophile and it comes and replaces chlorine. So what's going to happen, our transition state is basically a carbon that is a bond with incoming nucleophile and a breaking bond with outgoing leaving group. And this is just the primary alkyl halide. So we are going to have transition state like this. So this is the best because we still have CH3, but it's not the worst because we still have two hydrogen, not that in terms of electron density, just one CH3 group. So it's going to be the transition state.